Hello, let me introduce my name. My name is Venerana Baby Velatio. Special thanks to Miss Anna Fitriana SIMM as our lecturer for economic and businesses. This is our presentation about matrix.
The matrix concept. A matrix is the rectangular arrangement of numbers arranged in rows or columns present. Numbers are arranged into matrix or colored elements. Element matrix rows are horizontal structures, while columns are upright honest. The order matrix is the number of row elements and the number of column elements of a matrix. If a matrix has an I line and a column Z, then the matrix order AX. Z can be written by AIZ.
Alright, and now we're going to the example of the matrix concept. So if we look here, there's already a matrix that have inside the brackets, a big brackets, there's already 12 numbers. There's 1, 4, 1, 1, 3, 5, 4, 3, 6, 2, 1, 7. So I'm going to explain what my friends explained earlier. So there's a rows that is a horizontal structures. And then there's a columns. Columns is the one that vertical. So let us say that the first row is 1, 4, 1, 1 because it is horizontal and it is the top rows. It is the top one, so we call it as the first row. The second row is 3, 5, 4, 3, and the third row that means 6, 2, 1, 7. So that is the rows, y'all. And what is columns? Columns are the vertical one, is the upright one. So the first column we say it from the left, so it is 1, 3, and 6. It is the first column. The second column is 4, 5, and 2. The third column is 1, 4, and 1. The fourth column is the 1, 3, and 7. So let us say that what is the second row, the third column. So the second row, the third column. That means it is 4. Because why? Because the third column is 1, 2, 3, and 4, and that means that is the one that vertical here is the third column. And the second row 1, 2, 3, we get the second one and we get the answer, that is 4. Let us try again. The first column, the third row. Can you guess the number? Yes, it is 6. And let's get on to the next one.
Matrix addition and subtraction. Addition of two matrix can be added if the two matrices have the same order. The resulting matrix will also have the same order as the marking being added. The matrix component of the sum result of obtain adding up the component of each corresponding matrix. Consider the sum of the matrix of the order 2x2 below. Incremental A, B, C, D plus incremental E, F, G, H equals incremental A plus A, B plus F, C plus G, D plus H. In the addition of the matrix above, each matrix thus added up is of the same order of 2x2, and the result of the sum is also of the order of 2x2, the same as the order of the matrix being added. The row 1, column 1 component are obtained by adding the row, column 1 component in the first matrix, namely A, and the row 1, column 1 component in this second matrix, namely A, and so.
For the example of the 2 times 2 order, the addition matrix. So we got here, the first matrix is 4, -1, 3, and 2, plus 2, 1, -4, and 0. So what we're going to do is we're going to add them, add the values equals to the same row and the same column. So 4 plus 2, -1 plus 1, 3 plus -4, 2 plus 0. That's easy, right? So 4 plus 2 equals 6, -1 plus 1 equals 0. So we're going to write it in the first row, that is 6 and 0. In the second row, we see 3 plus -4, that gives us -1. So we write down -1 in the second row, the first column. Okay, get it? And 2 plus 0. 2 plus 0 means 2. So we write it down in the second row, the second column. So what we get here, the answer is 6, 0, negative 1, and 2. 6 is the first row and the first column. 0 is the first row and the second column. Negative 1 is the second row, the first column. 2 is the second row, the second column. So the matrix, the addition of the matrix is 6, 0, negative 1, and 2.
Subtraction reducing matrix are A by matrix B, written A. B is the addition of matrix A with the opposite of matrix B, namely B minus. The concept of subtracting a matrix is the same as adding a matrix. The condition for adding matrix also apply to subtracting matrix. Consider the following example of reducing matrix. Incremental A, B, C, D minus incremental E, F, G, H equals incremental A minus E, B minus F, C minus D, D minus H.
The example for the matrix subtraction, what we're going to do is actually the same with the addition one, but this one we minus it because it is subtraction. So we have an example here that is 4, negative 1, 3, and 2 minus a matrix that have 2, 1, negative 3, and 0. So what we're going to do, we're going to subtract it in the same row and the same column. So 4 minus 2, negative 1 minus 1, 3 minus negative 3, 2 minus 0. So 4 minus 2 equals 2. So we're going to put it in the first column and the first row. Negative 1 minus 1 equals to negative 2. We're going to write it in the first row, second column. Okay, so 3 minus negative 3, that gives us 6, because when negative meets minus, it becomes positive. So that is 6. We write it in the, can you guess it? Yes, we write it in the second row, the first column. And 2 minus 0, that gives us 2. We write it in the second row and the second column. So what we got here, the total of the subtraction of the matrix is 2, negative 2, 6, and 2.
Multiplication matrix. The multiplication matrix is the value in the matrix that can be generated by multiplying each row by its column that has the same number of rows. Each member of this matrix will later be multiplied by member of other matrix elements. Multiplication of matrix is carried out according to the order and rules that have to adding matrix number. The multiplication of these two matrices can be done when the number of column A and the number of rows B are the same. The matrix multiplication will produce a matrix with the same number of rows between matrix A and B. For clarity, see the description below. V equality equals incremental A, B, C, D, incremental H, E equals incremental AX plus BX CIA plus DE.
So we have example here, P matrix times Q matrix. So P matrix is equals to 3, 6, 2, and 4. Q matrix is 1, 2, 4, 5. So what we're going to do, we're not going to times it rows with rows, columns with columns. No, we're not going to do that. We're going to do is we times rows with columns and columns with rows. So that's the twist. It is a bit different. So we're just going to get into it. The first, so if you can see here, what we're going to do is we're going to write the first row. So the first row from P matrix is 3 and 6. So we're going to times it with the first column of Q. So 3 times 1. 3, that is the first row from the P matrix, and 1, that is the first column of Q matrix. So 3 times 1 plus. So the first row of P matrix is 3 and 6. So 3, we already said that 3 times 1, and now 6 times 4. 4 is from the first column in the Q matrix. So to make this more clear, we're going to make sure the first row of P matrix is 3 and 6. The second row of P matrix is 2 and 4. Now, we're going to look for the column. So the first column of Q matrix is 1 and 4, and the second column of the Q matrix is 2 and 5. So we're going to times them. So we already get the 3 times 1 plus 6 times 4. Next, we're going to times the first row of P matrix with the second column of Q matrix. So it is 3 times 2 and 6 times 5. Now, the answer we got for the first row. Now we're going to search for the second row in the answer. So earlier we've done with the first row from the P matrix. Now we're going to get into the second row of the P matrix, that is 2 and 4. So 2 we times with the first column of Q matrix. So 2 times 1 plus 4 times 4. That is the same. So we're going to times the second row from P matrix with the second column of Q matrix. So 2 times 2 and 4 times 5. Now we already get the number that we're going to times with. So we got 3 times 1 equals to 3 plus 6 times 4 equals to 24. And 3 times 2 equals 6 plus 6 times 5 equals 30. 2 times 1 equals 2. 4 times 4 equals 16. 2 times 2 equals 4. 4 times 5 equals 20. So what we're going to do, there's an addition. So we're going to add 3 with 24, 6 with 30, 2 with 16, 4 plus 20. And we get the value, the new answers of P matrix times Q matrix. That is 27, 36, 18, and 24. Now, so we see here, 27 is the first row and the first column. 36 is the first row and the second column. 18 is the second row and the first column. And 24 is the second row and the second column. So that is the answer. Now, let's move on to the next.
Okay. Hello everyone, my name is Mary and Danny. Okay, I'm here to explain about transpose matrix, determinant matrix, inverse matrix, and Cramer rule. Okay, first, about transpose matrix. The translating of the matrix refers to the new matrix obtained by transforming the first row of test into column of the new matrix. Transpose the matrix is the new matrix gained from an original matrix that alternates between column and file element. If it is known that a matrix with the order m kali n, it transposes. The matrix the by-lines transposes matrix new where the first column element equal first line element the matrix. Element of the second column, element of the second row, matrix A, element column thread equal thread line element a matrix.
Now, transpose matrix. So my friend already explained that transpose matrix is the new matrix gained from an original matrix that alternates between column and file elements. So for the examples we have A matrix equals to -5, 6, 6, and 9. So this only have one column with 4 rows, but when we transpose it, it's going to be 4 columns with 1 rows. That is -5, 6, 6, 9. But it's still the same value of number, but it is changed, the rows and the columns. So it is easier because we can write down from the top, from the most high. So -5, it is from the top. We are going to write it down, we transpose it from the left. So -5 still in the first one, but we write it from the left. So we're going to write it from the left to the right. And to make it more clear, I guess, we're going to look for the other example, that is B matrix with more numbers. There's 6, 5, 4, 9, 3, negative 7, 3, 5, 4, 4, 6, negative 1. So what we're going to do is we're going to transpose it. So if we see here, there's 3 rows and 4 columns. But when we change it, there's going to be 4 rows and 3 columns. So let's state it that the first row is 6, 5, 4, and 9. The second row is 3, negative 7, 3, and 5. The third row is 4, 4, 6, and negative 1. So we're going to transpose it. It's going to be, we're going to start from the most left, that is the first column. We're going to transpose it, become the first row. So the first column, we have 6, 3, and 4. That's going to be our first row after we transpose it. So 6, 3, and 4. That leaves to the next. So the right from the from the left to the right. So after 6, 3, and 4, we can move to the 5, negative 7, and 4. And we move to the 4, 3, and 6. We move again to the 9, 5, and negative 1. So you see here, it actually changed. The first one, it have 3 rows and 4 columns, but now it becomes 3 columns with 4 rows. Okay? And the other example for you, there's C matrix that have 3 rows and 3 columns. So it is 3, 4, 8, 7, 6, negative 5, negative 4, 6, 4. So the first row is 3, 4, 8. The second row is 7, 6, negative 5. The third row is negative 4, 6, and 4. When we transpose it, we're going to look for the first column. We move, become the first row. So the key to this transpose is we look for the column. So yeah, let's do it. So 3, 7, negative 4 becomes the first row. 4, 6, 6 becomes the second row. 8, negative 5, and 4 becomes the third row. And it is changed also when we transpose. The columns also change. The after transpose columns becomes 3, 4, 8, 7, 6, negative 5, negative 4, 6, and 4. It is different. It's always different. But there's a situation. If the transpose operation on a matrix resulting the additional matrix, then the matrix is called a symmetrical matrix. For example, we have here A matrix. It has 3 rows and 3 columns. That is negative 1, 7, 8, 7, 9, negative 5, 8, negative 5, 4. When we transpose it, it's still negative 1, 7, 8, 7, 9, negative 5, 8, negative 5, and 4. It is the same because it has same value number when we put it. So the rows and the columns have the same situation. So when we transpose it, it's still the same. Note this, all symmetric matrices are square matrices. There's never been other than square matrix. So yeah, let's move on to the next.
Okay, next about determined matrix. What is determined matrix? Determined matrix can be denoted by that open brackets A close brackets or A determinant or the particular function the connect a real number with a square long matrix. At square matrix or square the max has a determined value of the matrix is scalar. If the determinant of the matrix is equal to 0, then the matrix is called a singular matrix. To determine the determinants of the matrix, the order 2 kali 2 and the order 3 kali 3 give us 2 rules. Determine order 2 kali 2. The determined matrix square with the order 2 kali 2 can be calculated the following way. Okay. That open brackets A close brackets equal ACBD equal A kali D minus B kali C. Okay, next determine order 3 kali 3. The determinant of the square matrix of the order 3 kali 3 can be calculated in 2 ways, namely the SIR MUS rule. SIR rule and cofactor explanation. But the way that is often used to determine the determinant of the 3x3 order is the SIR rule. Step to define the determinant of the 3x3 matrix using the SIR rule. 1. Place the first column, the second column to the right of the determinant variable line. 2. And add the product of the element the R1 on the main dialog to the product of the element that are parallel of the main diagonal in the right direction. The subtract the sum parallel of the side diagonal. Oke, the rumusnya ini ya, contohnya.
Now, determinant matrix. So earlier I stated that the multiplication matrix is a bit tricky, but now this is more trickier because this is a bit different from others. It has to make some crossing multiplication. So, for example, we have here a matrix 3, 4, 0, negative 2, 1, 5, negative 1, negative 3, and 2. So, to find this determinant matrix, we have to do is we make the third column become the center. So what we're going to do is we get the other two columns, the first and the second column, we put it, we doubled it, we copy and we paste it on the beside of the third column. So it became 3, 4, 0, 3, 4, negative 2, 1, 5, negative 2, 1, negative 1, negative 3, 2, negative 1, negative 3. And what we're going to do now is we're going to cross multiplication. It's what I said. So we times 3 from the upper left, so we're going to times it crossing. Yeah. And when we times this, there's only two numbers that didn't get times. That is the first column, the second row, and the last column, the second row. So we're going to just multiply it with like this. So as I said earlier, we times it crossing. So 3 times 1 times 2. To make it more easier, we're going to start from left to the right. And later maybe we could start from the other side. So 3 times 1 times 2, 4 times 5 times negative 1. 0 times negative 2 times negative 3. So now we have to times it 3 numbers. So we can't times it only 2 numbers. It has to be 3 numbers because the order is 3 times 3. And yeah, so because we can't times 3 with 1, so we're going to move from the other side. We could use from the left side to the right side, but now we're going to start from the center. That is 0 times 1 times negative 1, 3 times 5 times negative 3, 4 times negative 2 times 2. So why I said this is more trickier, because you have to be detailed, you have to watch carefully when you times it, because it is more difficult if we times it crossing, because we could slip and we could get wrong numbers. So it is more trickier and we have to watch it carefully. So after we times it all, we get 6 plus negative 20 plus 0 minus negative 45 minus negative 16. That gives us 2. Negative 14 plus 45 plus 16. And the answer for the A matrix determinant is 47.
Okay, next explain about inverse matrix. An inverse matrix is the upper side of the matrix, by which the matrix is multiplied by the kin. Become an identity matrix. Inverse matrix symbolized by an A minus 1, A matrix. A matrix side to have an inverse if the determinant of the matrix is not equal to to 0. To determine the inverse of the matrix, there are 2 rules by the ordinance, the order 2 kali 2 and the order 3 kali 3. Inverse matrix order 2 kali 2. Inverse square matrix with the order 2 kali 2 can be so in the following ways. A pangkat minus 1 equal 1 per A dikali ADJ A with the provision of A equal 0. If A equal ABCD, so A pangkat minus 0 equal 1 per AD minus BC dikali A minus 1 per AD minus BC semicolon D minus A minus B A with A equal 0. Inverse matrix order 3 kali 3. Looking for the matrix inverse on the order 3 kali 3, we can use Gauss-Jordan method of the elimination. Systematically, the elimination of the Gauss-Jordan way stated of the follow: A1. The example: a square matrix Y elimination using the algebraic operation of establish and identity matrix operation carried out the matrix are also performed on the identity matrix, so that if a matrix become an identity matrix, then the identity matrix will roll into an inverse of the matrix.
Inverse matrix. This one is more tricky than the previous one we explained. It has its own formula, and my friends have already explained it earlier. The formula is A with the power of number -1 equals to 1 by A times D minus B times C times D negative B negative C times A. So we are going to jump in to the example. A matrix equals to 2, 3, 3, and 5. So 2 as A, 3 as B. The other 3, that is from the first column and the second row, that is C, and 5 as D. So we're just going to input the number to the formula my friends explained earlier. So it is 1 by 2 times 5 minus 3 times 3. So for the times D minus negative B, negative C, and A. So it becomes 5, negative 3, negative 3, and 2. So it actually a switching between A and D. So the earlier one, we have A 2 and D is 5. So we're going to switch the positions between A and D, and that becomes 5, negative 3, negative 3, and 2. So negative 3 is actually from the formula, because the formula stated that B and C become negative. So that's what we got. And now we're going to times it, and it became 1 by 10 minus 9. We times 5, negative 3, negative 3, and 2. And 1 by 10 minus 9 becomes 1 by 1 times 5 times 5, negative 3, negative 3, and 2. 1 by 1 is equals to 1, and 1 times the matrix, it gives us 5, negative 3, negative 3, 2. So that's the answer for the inverse matrix.
Okay, next, about Cramer rule. What is Cramer rule? The cumulation rule of the Cramer rule is the type from the inventor name, namely Gabriel Cramer. It's a formula that can be used to solve the linear equation system. The method uses a determinant factor of the matrix and other matrix obtained by replacing one of the column the factor consisting of the number to the right to the equation. For more details, I will use the Cramer rule to solve the matrix of the two linear variables of equation. Open brackets SPLDV and the three linear variable system equation open brackets, SPLTV. Well, consider the two variable system of the linear equation. A pangkat bawah 1 plus B pangkat bawah 1 Y equal C1 and A2 X plus B2Y equals C2. Using the elimination method, the value of the will be obtained, which is the follows. Okay, the example picture. Not how to write the results obtained above in the form of the determinant matrix. Next picture. Okay, to determine the matrix sought not to be worth 0. If D equal 0, then the value of the x and y become undefined because seen in the formula above, we cannot divide d, x, and dy by a 0. Okay, that's all. Okay, that's all the explanation from me. For a deeper understanding of the material, my friend will explain it. Okay, thank you and see you.
Alright, the Cramer's rule. This one is the most trickiest because it includes linear equation. And my friends already explained the formula earlier, so let's jump right in to the example. So we have here 2x minus 3y equals negative 13. X plus 2y equals 4. So we have this linear equation. What we're going to do is we make it into the matrix. So the first one, we're going to get the number. So 2x, that gives us 2. Negative 3y, that gives us negative 3. And x, that gives us 1. 2y gives us 2. So the first bracket or the matrix is 2, negative 3, 1, and 2. And there's also x and y, so we're just going to put in them the bracket as x and y equals to negative 13 and 4. So what we're going to do is we're going to look for the d, and that is we're going to include the matrix number, that is 2, negative 3, 1, and 2. So what we're going to do is we're going to times 2 times 2. We're going to times it crosswise. So 2 times 2, negative 3 times 1. It gives us 2 times 0 is 4, plus negative 3 times 1 is negative 3. So 4 minus negative 3, that becomes 4 plus 3, that gives us 7. And so what we're going to do next is we're going to look for the x's. And what we're going to do is we put the negative 13 and negative 3, 4 and 2. So the negative 3 and the negative 2 is where we got from the side, from the second column from the matrix we already got, from 2, negative 3, 1, and 2. So negative 13 and 4 times we're going to times it. Negative 13 times 2 minus negative 3 times 4, that gives us negative 26 plus 12 equals to negative 14. And we're going to look for the y. So y is different. What we're going to include the first column from the 2, negative 3, 1, and 2. It is 2 and 1. And we're going to put the negative 13 and 4 also. So it is 2, negative 13, 1, and 4. And we times it cross. So 2 times 4 and minus with negative 13 times 1. And it gives us 8 plus 13 equals 21. So to look for the x's is dx by d, that is negative 14 by 7, that gives us negative 2. And y, we look as dy by d equals to 21 by 7, that is 3. To check if this answer is correct, we could put the x and y into the equation. So 2 times negative 2 minus 3 times 3, that gives us negative 13. That is correct. So negative 2 plus 2 times 3 equal to 4. And that is correct. So that's all for the example of Cramer's rule.
So for my part, I'm in charge of 5 examples and its explanation about the matrix. So for the first example, we have to find those inverse matrix of C, which we can symbolize inverse. It was power of -1 that equals to 1 per determinant of C, which determinant it was the main diagonal minus with the side diagonal, then times with the A and B, we switch it, and the minus at the B and the C, we have to minus those. So the way how we do it is C power of -1 equals to 1 per the main diagonal. It was -3 times 2, so it was -6 plus minus 5 times 1, it was -1. So -6 plus 5. Then for the matrix, we have to switch the A and the B position. So we can make those into -3. Then for the B and C, we have to minus those. So the -5, we minus it. We times with the minus, so it remains 5. Then for the C, it was -1 because from the equation before it was -C, so it becomes -1. And for the D part, we switch it from before, it was 2, so it remains 1. So it remains -1 times -3, 5, -1 and 2. So it the conclusion, it was the matrix of C. It was 3, -5, 1, and -2. So for the second example, we have to find those matrix of S, which as it was the P, then power of 2 minus Q. For the P power of 2, we have to times it those, which it was 0 times 0 plus -2 times 1. Then for the next one, it was 0 times 2 plus -2 times 5. And for the next one is 1 times 0 plus 5 times 1. Then for the last one, it was 1 times -2 plus 5 times 5, which it remains for the P power of 2. It was -2, -10, 5, and 23. And for the last part, we have to solve it, which the matrix of S, it was P power of 2 minus Q, which it remains -2, -10, 5, and 23, minus -7, 1, 3, and 1. So it remains for the matrix of S, it was 5 from the -2 -7, and it was 5. And for the second one, it was -10 -1, which it remains -11. 5 minus 3, it was 2. Then 23 -1, it was 22. So the matrix of S, it was 5, -11, 2, and 22. So for the third example, we have to find those matrix of DP, which it's already shown the matrix of D and the E. So because of it was matrix 3 times 3, so the way how we do it is the A, B, and C times with the other matrix. It was from the A, D, and G. So we have to times those upper one and then the lower one. So the way how we do it is 1 times 5 plus 3 times 1 plus 4 times 8. Then for the next one, the B one, it was 1 times 4 plus 3 times 3 plus 4 times 6. For the next one, 1 times 7 plus 3 times 2 plus 4 times 9. For the next one, for the D, it was 6 times 5 plus 5 times 1 plus 2 times 8. For the E1, it was 6 times 4 plus 5 times 3 plus 3 times 6. For the F1, it was 6 times 7 plus 5 times 2 plus 2 times 9. For the G, 7 times 5 plus 3 times 1 plus 6 times 8. For the H1, it was 7 times 4 plus 3 times 3 plus 6 times 6. And for the last one, it was 7 times 7 plus 3 times 2 plus 6 times 9. Then it remains the matrix of DE. It was 40, 37, 49, 51, 51, 70, 86, 73, and 109. Fourth example, we have to find those matrix of M if M it was 2 times K minus transpose of L. So for the 2K, it was 2 times the matrix of K, which it remains 2 times 5, it was 10, 2 times 6, it was 12, 2 times 1, it's 2, and 2 times 3, it's 6. So 2K, it was 10, 12, 2, and 6. And for the transpose of L, it was, we changed those column or bar from the diagonal into the vertical. So it remains 1, 5, 2, and 3. And for the last part is we get those 2K and the L transpose to the equation of M equals 2. So it remains 10 minus 1, it was 9. 12 minus 5, it was 7. 2 minus 2, it was 0. And for the last one is 6 minus 3 is 3. So it remains the matrix of M, it was 9, 7, 0, and 3. For the last example, we have to find those X and Y. Then we can add those. For the X, we have the equation which it was X minus 2 plus 8 that equals to 20. So it remains X equals to 20 plus 2 minus 8. Then it remains the X, it was 14. So for the finding the Y, it was 3 plus Y equals to minus 8, which it remains the Y, it was minus 8 minus 3, which it remains the Y, it was minus 11. So the X plus Y equals to 3. Then that's it for our presentation about matrix. Thank you and goodbye.